If you've ever tried to manage modern cloud infrastructure, you probably know the feeling I'm talking about.
Oh, yeah?
It's like you're suddenly the mayor of this huge, sprawling city
Mm-hmm.
that's just being built, brick by hand.
Totally manual. Clicking through screens.
Exactly. Every time you need a new road, maybe upgrade a hospital, you're lost in these endless menus, just hoping like you didn't miss one single checkbox.
Right. And that feeling of fragility, like
Hmm.
you hit deploy and just hold your breath.
Yeah.
That's the classic symptom. You've got infrastructure, but no real blueprint.
It's manual chaos. Every little change feels super risky, like the whole city could just collapse.
And 6 months down the line, you look back and realize half your servers are configured differently.
Oh, nightmare.
Trying to replicate that for testing, forget it. It's like artisanal infrastructure building,
Yeah.
high risk, handmade. It just doesn't scale.
It really doesn't. So that's why we're here today. We want to introduce the master planning system for all this chaos. It's called Terraform. Oh. This tool basically takes that digital sprawl, all that complexity, and turns it into these organized, repeatable blueprints, version controlled.
It's the difference between, say, building a shantytown versus designing a proper, scalable city grid. Huge difference.
Exactly. And our mission today for this deep dive is to really demystify Terraform. It's a critical piece of the puzzle for anyone in DevOps or cloud engineering.
We're going to break down, 13 essential components?
Yep, 13 key parts.
And we'll use this one core analogy all the way through to make it stick.
The city planning analogy.
Exactly. Terraform is your city planning system, and you, listening right now, you're the mayor.
Love it. And our goal isn't just to define jargon. We want to give you the strategic thinking behind it, how to actually deploy and manage infrastructure like a pro.
We're aiming to take you from maybe feeling confused or intimidated to having real clarity, expert clarity even.
Okay, let's do it. Where do we start? What's the absolute foundation?
Right, so the big idea underpinning everything is infrastructure as code, IAC. We need to talk about why this is so much better than the old way.
The old way being clicking around in a GUI, or maybe writing tons of manual shell scripts.
Precisely. That manual path, it just introduces so much variance. If two engineers try to build the exact same server by hand.
They'll inevitably do it slightly differently, a setting here, a configuration there.
Exactly. And that leads to inconsistent environments. Things break.
Oh.
You don't know why. It's a recipe for disaster, really.
Okay, so IAC solves that. How?
With IAC, you're managing everything, your networks, databases, firewalls, all of it, using code files, simple text files.
Code files.
And this gives you 3 huge benefits: consistency, version control, and automation. Let's break those down.
Okay, consistency first.
Consistency means if you run the code today, or 6 months from now, or a year from now, the outcome is identical every single time. It just eliminates that human configuration drift.
Makes sense. No more, well, it worked on my machine kind of problems.
Exactly. Then version control. This is huge, especially for things like auditing and rollbacks.
Right, like Git for your infrastructure.
Precisely. If something goes wrong, say an outage happens after a deployment, you can literally roll back your infrastructure to the last known good state, just like rolling back software code.
And you have a history, right? You know who changed what, when they changed it.
Full audit trail. That's something manual changes just can't give you reliably.
Okay, so consistency, version control. What was the third?
Automation, which really means scalability.
Ah, okay. So if suddenly your company lands a massive new client.
Right. And you need, say, 10 identical staging environments spun up, like yesterday.
Instead of a week of frantic clicking.
You just run the IAC code 10 times. Boom. Instant, repeatable environments. That's the power of automation here.
Okay, I'm sold on IAC. So if we're managing infrastructure with code, we need a language for these. Blueprints, you call them. What's the language the mayor speaks?
Terraform uses HCL. That stands for HashiCorp Configuration Language.
HCL.
It's designed specifically for infrastructure, so it's meant to be really human readable. You look at it, and it should make sense what it's trying to build.
Easier than reading, say, complex XML or JSON sometimes.
Generally, yes. But the most important thing about HCL and Terraform's approach, the real efficiency engine, is that it's declarative.
Declarative. Okay, this sounds like one of those key concepts we need to really nail down. What does that actually mean? How is it different from, well, other ways, imperative ways?
Great question. Let's think about the city planning again. If you're an imperative planner, you give step-by-step instructions. You dictate the how.
Like, step 1. Lay the foundation for this building. Step 2, put up the walls. Step 3, connect the water line.
Exactly. You're specifying the sequence of actions. Tools like maybe Chef, Puppet, or even detailed Ansible playbooks can work this way. They manage the process of configuration.
Okay, so that's imperative. What about declarative?
Declarative is different. With Terraform, you don't specify the steps. You just declare the desired end state.
The end state.
You tell Terraform, I want 10 blue houses in this part of the city, and they need to be connected to network Z.
That's it. And Terraform?
Terraform looks at your desired state, the 10 blue houses, compares it to the current reality, what's actually built.
Okay.
And then it figures out the most efficient sequence of steps, the how, to get you there.
Ah, so it's managing the outcome, not the process steps.
Precisely. That's why tools like Terraform simplify things like state management.
Yeah.
They don't need to track every single command executed, just the final goal. The complexity of provisioning, figuring out the right order. Terraform handles that internally.
So the mayor, me, I can just focus on the high-level design, what I want the city to look like.
That's the idea. It's much more efficient.
Yeah, I can see that. If I already have, say, 8 blue houses, and I change my blueprint to say I want 10.
Terraform just calculates, okay, need to build 2 more. It doesn't rerun instructions for the 8 that are already fine. It just figures out the delta, the difference.
Much smarter. Okay, so the mayor has the blueprints, written in HCL stating the desired city. What happens next? We need someone to actually build it, right?
Exactly. You need construction companies. And importantly, companies that know how to build on different terrains, AWS, Azure, Google Cloud, maybe even on-premise stuff.
Okay.
These specialist construction companies, in Terraform language, are the providers.
Providers, got it, like specialist vendors.
Yep, they're the crucial middleware. They know how to take your generic HCL blueprint and translate it into the specific proprietary API calls that each cloud platform understands.
So if I'm building on Azure, I need the Azure provider.
You use the Azure provider, yeah. If you're managing DNS with Cloudflare, you use the Cloudflare provider. If you're deploying to Kubernetes, there's a Kubernetes provider.
And Terraform figures out which ones I need.
Well, you declare them in your configuration. And then when you run Terraform in it, we'll get to that command later, Terraform downloads the specific providers you've requested. It gets the right version, sets up the communication layer.
Okay. Now, here's something I find really interesting about Terraform. Its ability to work with multiple clouds.
Ah, yes. The multi-cloud capability. This is a huge differentiator.
Because Terraform, the mayor, can hire any of these construction companies, right? AWS provider, Azure provider, GCP.
Any combination you need. This is fundamentally different from platform-specific tools. Like AWS CloudFormation only knows how to build on AWS. Azure Resource Manager only knows Azure.
They're like contractors locked into one city. They can't work anywhere else.
Exactly. Terraform is vendor agnostic in that sense. The mayor is free to choose the best provider for the job, regardless of the underlying platform.
And the big advantage there for, say, a development team.
They learn HCL once, they learn the Terraform workflow once, and then they can manage infrastructure across AWS, Azure, GCP, Kubernetes, whatever, using the same language and tools. That consistency is incredibly valuable, especially in hybrid or multi-cloud setups.
Okay, it makes total sense.
Sure.
So we have the mayor, the HCL blueprints, the provider construction companies. What are they actually building? The individual things in the city.
Right, those are the resources.
Resources.
A resource is basically any building block of your city, any piece of infrastructure managed by a provider.
Okay, let's ground this. You mentioned Azure earlier. What are some examples of Azure resources in Terraform terms?
Sure. Let's use the Azure provider, Azure terminology. You might define an Azure virtual machine.
Which, in our analogy, is a house, a server.
Yeah, think of it as a house, a specific place ready to host your application, your server workload.
Okay, what else?
You'll definitely need an Azure virtual network. That's like the city's main road system. It defines how all your buildings, your VMs, can talk to each other.
And presumably you need the roads before the houses.
Generally, yes.
Yeah.
Terraform usually figures out those dependencies, but fundamentally, you need the network first.
Got it. What about utilities? Data storage, security.
Good examples. An Azure storage account could be your city's water storage tank, holds data securely.
Oh, yeah.
And for security, something like Azure Key Vault. That's like the super secure bank vault for storing all the city's secrets. API keys, passwords, certificates, absolutely critical.
So each of these resources, the VM, the network, the storage, the vault, is defined in my HCL blueprint.
Exactly. You define the resource type, give it a name, and then specify all its desired properties. Its location, region, its size, maybe specific configuration settings.
And those definitions are what the provider uses to make the actual API calls to Azure or AWS or wherever.
Precisely. The HCL is the intent, the provider is the translator, and the resource definition contains the specific instructions for that translation.
Okay, so defining all these resources in the blueprints, the HCL files, that's step one. But just having the plan isn't enough, right? You need to know what's actually been built.
Absolutely critical. If you don't keep a perfect record of what's been successfully constructed, managing changes becomes impossible, or worse, dangerous.
And this brings us to something that sounds, well, maybe a bit complex, but foundational in Terraform: state management.
It is foundational, probably the most important concept to grasp after the basics. Let's talk about the state file.
The state file, okay.
What is it? By default, it's a file named terraform.tfstate. Think of this as the official city registry.
The city registry, like the land registry office?
Exactly like that.
Yeah.
It is the single authoritative source of truth about your infrastructure as managed by Terraform. It's a snapshot of every single resource Terraform has successfully deployed and is currently keeping track of.
Okay, single source of truth. And what's its main job? Why is it so important?
Its function is massive. When you, the mayor, issue a new blueprint or modify an existing one, Terraform uses this state file to do a critical comparison.
A comparison between?
Between the desired state, what your HCL code says you want, and the current state, what the state file says is actually built and managed right now.
The diff. It figures out the difference.
Exactly. This comparison lets Terraform be incredibly intelligent and efficient. It stops it from rebuilding things unnecessarily. If a resource already exists and its configuration in your HCL hasn't changed, Terraform sees that in the state file and just leaves it alone.
Makes sense. Don't fix what isn't broken.
Right. And maybe even more critically, the state file records important metadata that isn't even in your HCL code,
Like what?
like the actual unique IDs assigned by the cloud provider when a resource was created, or intricate dependency information. Terraform remembers that this VM depends on that network interface, which depends on that subnet.
Stuff you need to manage changes but wouldn't necessarily write in the blueprint itself.
Precisely. It maps your logical resource names in HCL to the real-world resources.
Okay, but having this central registry, it sounds powerful, but it also sounds like it could introduce problems if it gets out of sync with reality.
You've hit on the nightmare scenario, drift.
Drift? What is that exactly?
Drift happens when your actual infrastructure in the cloud gets modified outside of the Terraform workflow.
Meaning, someone logs into the Azure portal directly and changes something manually.
Exactly that. An engineer goes rogue, or maybe just makes a quick fix and manually resizes a VM or tweaks a firewall rule without updating the Terraform code or state.
So the city registry says we have 10 houses, all perfectly configured.
But someone snuck in overnight and, I don't know, demolished 2 of them, or maybe added a new window without telling the mayor's office. The registry is now wrong. Reality has drifted.
And what happens when Terraform runs next?
When you run Terraform plan again, Terraform doesn't just trust the state file blindly. It also makes API calls to the actual cloud provider to check the real status of the resources it thinks it's managing.
Okay, so it compares the blueprint, the state file, and reality.
Yes, it compares reality from the API calls to what the state file says reality should be. If there's a mismatch that's drift, it detects it. It will propose changes in the plan to reconcile the difference. It might try to delete the manual change you made or recreate the resource that was manually destroyed to force reality back into alignment with the configuration code.
So detecting drift is crucial for keeping things consistent.
Absolutely. Undetected drift undermines the whole point of IAC.
Okay, so this state file, this city registry, it sounds incredibly important. We absolutely cannot lose it or corrupt it.
Correct. Which is why keeping it just on your local laptop, while fine for learning or solo experiments, is a really bad idea for teams or serious projects.
Why? What are the risks?
Well, loss, obviously. Your laptop dies, the state file is gone. Corruption is another risk.
Right.
But the biggest issue for teams is collaboration. How do multiple engineers work on the same infrastructure if the state file is only on one person's machine?
Yeah, impossible. You'd constantly overwrite each other's changes.
Exactly. So the solution, and it's pretty much essential for any professional setup, is remote state.
Remote state, meaning we don't keep the terraform.tf state file locally.
Right. You configure Terraform to store the state file in a shared remote location, a central city registry office, basically.
Like what kind of location?
Typically, it's highly available, durable object storage. Think Amazon S3 buckets, Azure storage accounts, Google Cloud storage, Services designed for high reliability.
So everyone on the team points their Terraform setup to that central location.
Yep. Ensures everyone is working off the same up-to-date registry.
And beyond just accessibility, I assume there are security benefits too, or considerations.
Huge security considerations.
Yeah.
The state file can contain sensitive information about your infrastructure topology, maybe even some output values that are sensitive.
Right, you wouldn't want that just lying around.
So when you set up your remote backend, you absolutely must ensure proper access controls are in place. Who can read it? Who can write it? And crucially, you need to enable encryption at rest for the storage backend itself.
So even if someone somehow got access to the raw storage, the file itself is scrambled.
That's the goal. Secure the bucket. Secure the file within the bucket. Defense in depth.
Okay, so remote state solves the sharing and backup problem. But what about the collaboration issue? If two engineers try to run Terraform, apply at the exact same time, pointing to the same remote state file.
Yeah, that's the other critical piece, state locking.
Locking, like locking a database record.
Exactly like that.
Yeah.
Without locking, imagine engineer A starts an apply. Terraform reads the state, calculates changes, starts making API calls.
Okay.
But before engineer A finishes and updates the state file with the results, engineer B kicks off their apply. They read the old state file, calculate their changes, and start applying them.
Oh, wow. Chaos. You'd end up with a completely messed up state file reflecting neither set of changes correctly.
Total corruption. A half-finished city based on conflicting plans. State locking prevents this.
How does it work?
Before Terraform starts any operation that might modify the state, like apply or destroy, it tries to acquire a lock on the state file via the remote backend.
And if it gets the lock?
It proceeds. While it holds the lock, if engineer B tries to run apply, Terraform will tell them, state is locked by engineer A. Please try again later.
So only one person can modify the registry at a time?
Correct. It ensures atomic updates to the state. Many remote backends offer this capability. For example, using Azure Storage often involves using the BLAS leasing mechanism. With AWS S3, you often use a DynamoDB table alongside it just for managing the locks.
Okay. What happens if something goes wrong? Like engineer A's process crashes mid-apply while holding the lock?
Good question. That can happen. The lock gets stuck or dangling. Now nobody can apply changes.
So you need a way to break the lock.
You do. There's usually a command, often something like Terraform force unlock, that lets you manually remove the lock. But you have to be absolutely sure that the process holding the lock is truly dead. Otherwise, you risk corruption by unlocking it prematurely.
Got it. So remote state for sharing and durability, state locking for safe concurrent operations, non-negotiable for teams.
Absolutely essential for any serious Terraform usage.
Okay. Foundation Secure City Registry is safe and shared. Now, as mayor, I want to scale. I don't want to write a totally custom blueprint for every single building or every neighborhood. How do I standardize and customize?
Excellent question. This is where we get into making our blueprints reusable and flexible. The first tools for this are variables and outputs.
Variables and outputs. Let's start with variables.
Think of variables as the parameters for your master plan. They allow you to define options or choices that can be changed each time you run the plan without actually modifying the core blueprint code.
So instead of writing build a small server directly in the code.
Right. You define a variable, maybe call it instance size, and then in your resource definition, you refer to that variable.
Something is in size small or something.
Well, you'd reference it like size var.instance size. Then when you run Terraform, you can provide a value for that variable. You can run it once, setting instance size to small for your dev environment, and then run the exact same code again, but set instance size to large for production.
So the code stays the same, but the input changes the outcome. It makes the blueprint flexible.
Exactly. It adheres to the DRY principle. Don't repeat yourself. You write the logic once and customize it with variables.
What about best practices for variables? Anything to keep in mind?
Definitely. Good practice is to give variables descriptions, explaining what they're for. You can also set default values, and crucially, you can add validation rules.
Validation.
Like ensuring the instance size variable only accepts valid sizes like small, medium, large, and rejects typos or invalid options. Or maybe ensuring a region variable is one of the approved regions your company uses. It adds guardrails.
Okay, that makes sense. So variables are inputs. What about outputs?
Outputs are the opposite. They're like the public city notice board. After Terraform builds something, outputs let you declare specific pieces of information about those resources that might be useful elsewhere.
Useful how?
Let's say you build a network. An output could be the ID of that network. Or if you build a load balancer, the output might be its public IP address.
Okay, so information from the built infrastructure.
Yes, and these outputs are essential for connecting different parts of your infrastructure together, especially when you break your configuration into smaller pieces.
How so?
That output from one Terraform configuration, maybe the one that builds your core network, can be used as an input variable for another Terraform configuration, say, the one deploying application servers into that network.
Ah, chaining them together. The network build outputs the network ID, and the server build consumes that ID as an input variable.
Exactly. It allows for clean separation of concerns while still enabling components to communicate and connect.
Okay, variables for input flexibility, outputs for sharing results. This seems like it would lead naturally into making bigger, reusable chunks of blueprints, right?
Perfectly.
Yeah.
That brings us to modules.
Yeah.
Modules are probably the most beloved feature for teams looking to scale Terraform usage effectively.
Modules. What are they, fundamentally?
Think of a module as a prepackaged, reusable neighborhood design.
A blueprint for a blueprint.
Kind of, yeah. It's a collection of interconnected resources,
Right.
VMs, networks, databases, etc., bundled together as a single unit, designed to perform a specific function. For example, you might have a module that defines your standard web application stack. One load balancer, two web servers, a security group, maybe a connection to a database.
So instead of defining all those individual resources every time, I just use the web stack module.
Exactly. The big benefit is abstraction. The complexity of how that web stack is actually configured is hidden inside the module.
And I, as the user of the module, just interact with.
Simple input variables that the module exposes. Things like app name, environment tag, maybe database endpoint.
Yeah.
You provide those high-level inputs, and the module handles the detailed resource creation.
That sounds amazing for standardization. If everyone uses the approved web stack module.
Then you guarantee every web stack deployment follows the company standards, security best practices, tagging convention, everything. It promotes consistency and drastically speeds up deployment. Need 10 microservices? Call the module 10 times with different inputs? Done.
Okay, but you mentioned pitfalls earlier. What's the big danger with modules?
The major pitfall is poor design, specifically around parameterization. If you create a module but hard code values inside it, like always deploying to us East 1 or always creating 3 servers,
Then it's not really reusable, is it? It's rigid.
exactly, it becomes inflexible. A well-designed module should be almost completely environment agnostic. It should take variables for everything that might conceivably need to change between deployments. Region counts, sizes, names, tags, network IDs.
And it should also have outputs, right?
Absolutely. It needs to output any information that downstream resources or other modules might need to know about what it just created, like the load balancer's DNS name or the server IDs. Good inputs and outputs are key to good module design.
Okay, so modules let us create reusable neighborhood plans. Now, how do we manage applying these plans to different parts of the city? Like, I need a development district, a testing district, and the main production downtown area. I don't want to mix them up.
Right. You need isolation between environments. Testing new, potentially breaking changes in production is a recipe for disaster.
So how does Terraform handle that separation?
The built-in mechanism for this is called workspaces.
Workspaces.
Workspaces allow you, the mayor, to manage multiple, distinct instances of the same infrastructure configuration using the exact same set of HCL blueprint files.
Same code, but different deployments.
Different deployments, isolated from each other. Think of them as separate districts. A dev district, a test district, a prod district.
And how does the isolation work? What keeps them separate?
Each workspace maintains its own completely separate state file.
Ah, the city registry is separate for each district.
Exactly. When you switch your command line context to the test workspace, any Terraform plan or apply command you run will read from and write to a dedicated test.tfstate file. Changes you make only affect the testing environment. Switch to prod, and you're working with prod.tfstate.
That provides the necessary isolation to prevent accidentally changing production when you meant to change dev.
That's the primary goal. It lets you use one code base to manage multiple environment instances.
Now, you mentioned this is the built-in mechanism. Is there another way people approach this? I think you hinted at something.
Ah, right. This is a point of discussion, maybe even debate, in the Terraform community, especially for managing production. While workspaces are great for managing non-critical environments like dev, test, staging, many experienced teams choose not to use workspaces for the production environment.
Why not?
It boils down to an extra layer of safety against human error.
How so?
With workspaces, you're still using the same directory, the same code files. It's relatively easy to accidentally pipe Terraform apply, auto-approve, while you think you're in the dev workspace, but you actually forgot to switch and you're targeting prod.
Ouch. Yeah, a single command could take down production.
Exactly. So the alternative strategy is to manage production infrastructure using a completely separate root directory structure.
Meaning a different folder on disk with its own copy of the relevant HCL files or modules reference.
Yes. And critically, its own separate remote state backend configuration, potentially even with different access credentials.
So you'd have to explicitly CD into the infraprod directory to manage production. It makes accidental cross-contamination much harder.
Much harder. It adds a very strong physical or logical separation. You can apply different permissions, different CI/CD pipelines, different approval processes to that production directory.
Okay, so let me recap the distinction. Modules are for creating reusable designs or components. Workspaces are for deploying the same design into multiple isolated environments, like dev, test, by using separate state files.
Correct.
But for the highest level of safety, especially for production, many pros prefer separating environments using distinct directory structures instead of, or in addition to, workspaces.
That's a very common pattern for managing risk, yes.
Because,
a key strategic decision for the mayor.
all right, we've got blueprints, providers, resources, state management, modules, workspaces. Now let's talk about the actual doing. What's the day-to-day workflow? How does the mayor initiate construction, review the plans, and get things built?
This is the core Terraform workflow. It revolves around 4 main commands, what I call the big 4. You'll use these constantly.
The big 4. Okay, what's the first one?
Everything starts with Terraform. Init. Initialization.
Init, like setting up the construction site headquarters.
That's a perfect analogy. When you run init in a directory containing Terraform code, it does a few key things. First, it scans your code to see which providers you need, like Azure, Oz, etc.
Okay.
Then it downloads the correct versions of those provider plugins. It also downloads any modules you might be referencing from external sources like the Terraform registry or Git.
So it gathers all the necessary tools and external blueprints.
Exactly. And critically, if you've configured a remote backend for your state file,
which we decided is essential.
it sets up the connection to that remote backend, like Azure Storage or S3, and prepares to rewrite the state file there. You generally only need to run init once when you first set up a project, or whenever you change providers, modules, or the backend configuration.
Got it. Step 1, what's next?
Next comes, arguably, the most important safety step. Terraform plan.
Plan? This sounds like drafting the next phase of construction.
Precisely. When you run plan, Terraform performs that comparison we talked about earlier. It reads the current state from your local or remote state file. It checks the actual state of resources in the cloud via API calls to detect drift, and it compares all that against your current HCL code, the desired state.
And the output is?
The output is an execution plan. It tells you exactly what Terraform intends to do to make reality match your code. It will list very clearly
resources to be added,
resources to be changed, and what specific attributes are changing.
And resources to be destroyed.
Yes. It gives you a plus for additions, a for changes, and a plain for deletions.
And this step doesn't actually change anything in the cloud, right? It's just a preview.
Correct. Terraform plan is purely read-only. It's non-destructive. It's your chance to review exactly what will happen before you commit to it. This step should absolutely never be skipped, especially not in any kind of automated pipeline.
It's the final human safety check. Does this look right? Is this really what I intended?
Exactly. The plan output also shows the dependency graph and figured out the order it will do things in. It's your blueprint draft versus the real build assessment.
Okay. Init, then plan. Assuming the plan looks good, what's the command to actually build it?
That's Terraform apply.
Apply. Makes sense. This is the execution phase.
This is the execution phase. When you run apply, Terraform essentially takes the plan it generated, or generates one if you didn't explicitly run plan first, though that's less safe, and starts making the necessary API calls to the providers.
The construction companies get to work.
They get to work building, modifying, or destroying resources according to the plan. This is where your code actually becomes reality in the cloud.
Okay, quick practical question here. What if apply fails halfway through? Say, Azure rejects a request because I asked for an invalid VM size or an API is temporarily down. Do I end up with a half-built city?
That's a great question. Terraform tries its best to be somewhat transactional, but cloud APIs aren't always perfect. If a specific resource creation or update fails, Terraform will usually stop the apply process at that point. It will record the resources that were successfully created or modified up to that point in the state file, but the failed resource and anything that depended on it won't be there or will be incomplete.
So the state file might be partially updated.
It might be marked as tainted or partially updated, yes. Terraform will release the state lock. You'll typically need to fix the error in your HCL code, like correcting the VM size, and then run Terraform apply again. Terraform will then look at the partially updated state, see what's missing or wrong based on the corrected code, and attempt to finish the job.
Okay, so it tries to recover gracefully, but you might need to intervene and rerun apply after fixing the issue.
Usually, yes. It won't typically leave you with completely orphaned resources it doesn't know about, but the apply needs to complete successfully for the state to fully match the desired configuration.
Got it. So init, plan, apply. What's the fourth command in the big four? Sounds like it might be the opposite of apply.
It is. It's Terraform destroy.
See, destroy. The bulldozers.
Exactly. This command does what it says on the tin. It reads your configuration and state file, figures out all the resources currently managed by Terraform in that workspace,
And removes them.
and removes them all. It effectively tears down the entire infrastructure defined in that configuration. Like apply, it first generates a plan showing everything that will be deleted, asks for confirmation, and then proceeds to make the deletion API calls.
Okay, that sounds powerful. And potentially dangerous.
Extremely dangerous if used incorrectly. We have to stress this. Never, ever run Terraform destroy casually, especially not against a production environment or workspace, unless you are absolutely 100% certain you intend to delete everything managed by that configuration. It's generally irreversible.
Used with extreme caution. Got it. So that's the big four. Init, plan, apply, destroy. Are there other useful commands for, say, maintenance or checking things?
Oh yes, several important ones for day-to-day quality and maintenance.
Like what?
Before you even run plan, it's good practice to run Terraform validate.
Validate. What does that check?
This is like the city inspector doing a quick check on your blueprints before you even propose them. It checks for syntax errors in your HCL, ensures all your variable references are correct, checks the structure. It's a very fast local check that catches basic mistakes early.
Good hygiene. What else?
Terraform FMT. That stands for format.
Ah, code formatting.
Exactly. It automatically rewrites your HCL files to a standard conventional style, consistent indentation, spacing, alignment. This doesn't change the logic, but it makes the code much more readable and consistent, which is crucial when working in a team. Everyone's code looks the same.
Run FMT before committing code. Got it. What about checking on that drift problem we talked about? If I suspect the state file is out of sync with reality.
There's a command for that. Terraform refresh. This command explicitly tells Terraform, go talk to the cloud APIs for all the resources listed in the state file and update the state file with their current real attributes.
So it resurveys the city and updates the registry without proposing any changes to the infrastructure itself.
Correct. Now, it's worth noting that Terraform Plan automatically performs a refresh as its first step anyway. But sometimes you might want to run refresh explicitly just to update your state file to match reality, perhaps before investigating something or making a manual change you intend to import later.
Okay. And what if I have a specific resource, say a virtual machine that's acting weirdly, and I just want Terraform to replace it with a fresh one on the next apply, even if my HCL code hasn't changed?
Ah, that's exactly what Terraform Taint is for.
Taint sounds bad.
It basically marks a specific resource instance in the state file as tainted or damaged.
Like putting a big X on a building scheduled for demolition.
Kind of. When you run Terraform Apply next, Terraform sees that tainted mark. It ignores the fact that the HCL code matches the existing, but tainted, resource. Instead, the plan will propose to destroy the tainted resource and then create a brand new one based on the current HCL configuration.
So it forces a replacement of that specific resource.
Exactly. Useful if a resource gets into a bad state that Terraform can't easily fix by just updating attributes.
Okay, that covers the main workflow and maintenance commands. Now, as mayor, I don't just want to build, I need rules. Regulations. How do I enforce citywide policies like no building can use more than X amount of power, or all houses must have fire escape?
Excellent point. You need guardrails.
Right.
In the Terraform ecosystem, this is often handled by policies.
Policies, how do they work?
These are separate rules, often written in a policy as code language like Sentinel from HashiCorp, or Open Policy Agent, OPA, which is a popular open standard.
Okay, and they integrate with Terraform.
Yes. These policy engines can analyze the Terraform plan before the apply happens.
Ah, so they act as a gate before infrastructure is changed.
Precisely. You can write policies like, fail the plan if any VM is created outside of approved regions, or ensure all S3 buckets have encryption enabled, or verify that all resources have a cost center tag.
And if the plan violates the policy?
The policy engine flags it, and typically the apply step is blocked. The plan fails the policy check. It guarantees compliance before anything gets deployed, which is much safer than trying to fix it afterwards.
That sounds incredibly powerful for governance and security. So those are broad city laws. What about rules for specific buildings or workers?
Right. In addition to broad policies, Terraform has lifecycle rules, which are special instructions you can add directly within a resource block in your HCL. They act like specific maintenance directives for that particular resource.
Like what?
One of the most common and important is prevent destroy. True.
Prevent destroy. Sounds like what it does.
It does. If you set this lifecycle rule on a resource, maybe your critical production database Terraform will refuse to destroy that resource. Even if you run Terraform destroy, or if a change requires replacing the resource, Terraform will throw an error saying destruction is prevented.
A crucial safety net for your most important infrastructure.
Absolutely. Another very useful one is create before destroy.
True.
Create before destroy. Okay, how does that help?
Normally, if Terraform needs to replace a resource, maybe you changed an attribute that requires replacement, its default behavior is to destroy the old one first and then create the new one.
Which means there's a period of downtime while the replacement happens.
Exactly. But if you set create before destroy true, Terraform reverses the order. It first creates the new resource alongside the old one. Once the new one is successfully created, it updates any references, and only then does it destroy the old resource.
Yeah, zero downtime updates, or at least minimize downtime, like building the new water tank and getting it fully operational before tearing down the old one. That's the perfect analogy.
Yeah.
Essential for critical services where you can't afford an outage during updates.
Very cool. Okay, one last thing in this section. We talked about dependencies, roads before houses. You said Terraform usually figures this out automatically.
It does remarkably well.
Yeah.
It builds an internal dependency graph based on how resources reference each other in your HCL code. If your VM resource definition refers to subnetted Azure subnet.mysubnet.id, Terraform knows it must create my subnet successfully before it attempts to create the VM. That's implicit dependency management.
But does it ever get it wrong? Or are there cases where the dependency isn't obvious from the code?
Yes, that happens. Sometimes resources depend on each other implicitly without a direct reference in the arguments. A classic example might be setting up an IAM role or policy and then needing that role policy to be fully propagated and available before another resource that uses it but doesn't directly reference its ID can be created successfully.
So Terraform might try to create the second resource too early before the permissions are ready.
It might. In these cases, where the implicit dependency detection fails, you need to provide an explicit hint. That's done using the depenson meta-argument.
Depenson.
You add depenson azure_role.myrole, for example, to the resource that needs to wait. This tells Terraform, do not even start creating this resource until my role has been successfully created. It manually adds an edge to the dependency graph.
So you use it sparingly only when Terraform can't figure out the order automatically?
Exactly. Rely on implicit dependencies first, but use depenson when necessary to enforce a specific order that isn't obvious from direct references.
Okay, we've got the workflow, the commands, the safety features. Now let's scale this up. Doing init, plan, apply manually is fine for one person, but for a team building a massive city, you need automation. You need the robot chef.
The robot chef, I like it. Yes, we need continuous integration and continuous deployment CI/CD. This is where the real power and scalability of IAC shines. We connect the Terraform workflow to automated pipelines using tools like GitHub Actions, GitLab CI, Azure DevOps, Jenkins, etc.
So every time code gets merged, the pipeline runs Terraform automatically.
That's the goal. The robot chef handles the init, plan, and apply steps consistently every single time. But as the mayor overseeing this automation, you need to implement strict safety measures. Automation without guardrails is how you get accidental disasters at scale.
Okay, what are the key best practices for Terraform in CI/CD?
Best practice number 1, absolutely crucial, separating the plan and apply stages.
Don't just run Terraform apply auto-approve.
These don't, especially not in production pipelines. The foolproof method involves a distinct separation. The pipeline first runs Terraform plan and saves the resulting execution plan to a file and artifact.
A binary plan file.
Yes, this plan file is then stored. The pipeline might pause here, waiting for human review and approval, or perhaps automated policy checks run against the plan file.
Okay.
Only if the plan artifact is approved does the next stage of the pipeline run. And that stage takes the exact same plan file that was reviewed and approved and runs Terraform apply using that specific file as input.
Ah, so you guarantee that what was reviewed is exactly what gets executed. No chance of the code changing between the plan and apply.
Precisely. It decouples the planning review phase from the execution phase, adding a massive layer of safety.
Okay, separation of plan and apply. Got it. Best practice, too. Must be security related.
You guessed it. Secure secrets management. We talked about the Key Vault resource, the city's bank vault. You absolutely cannot hard code sensitive information, API keys, database passwords, TLS private keys, directly into your HCL configuration files.
Even if the code repository is private.
Even then, it's just bad practice and increases the risk of accidental exposure. Your blueprint should describe the infrastructure, not contain the keys to the kingdom.
So where do secrets come from in a CI/CD pipeline?
You must use a dedicated secrets management solution. This could be Azure Key Vault, AWS Secrets Manager, HashiCorp Vault, or the built-in secrets management features of your CI/CD platform, like GitHub Secrets or Azure DevOps variable groups.
And Terraform retrieves these at runtime.
Yes. Typically, the CI/CD pipeline securely fetches the secrets from the vault and injects them into the Terraform process as environment variables. Terraform can then reference these environment variables to configure providers or resources without the secrets ever being written to disk in the HCL code.
Keep the bank vault combinations out of the public blueprints. Makes sense. Okay, best practice 3.
The final human safety net, approval gates, especially for production.
So even with plan apply separation, you want a human to explicitly say, go.
For production environments, absolutely. Between the stage that generates the plan artifact and the stage that applies it, you implement a manual approval step in your CI/CD tool.
And who approves?
That depends on the organization, but often it requires one or maybe two senior engineers or operations leads to visually inspect the plan output. Okay, it's proposing to change these 5 servers and add 1 database. That looks correct. And then click the Approve button before the pipeline proceeds to the Apply stage.
It's the final sanity check before the robotic bulldozers or cranes are deployed to the live city.
Exactly. It prevents those catastrophic outages caused by a simple typo, a misunderstood change, or a forgotten variable update that automation alone might miss.
Okay, plan apply separation, secure secrets, approval gates. That makes automated Terraform much safer. But even with all that, things can still go wrong. Let's talk troubleshooting. What are the common errors people hit?
Good idea. Let's cover the top 3 headaches you might encounter, especially in team environments. The first one is very common, the state lock error.
We talked about locking. This is when someone else is running apply or a previous run crashed.
Exactly. You try to run plan or apply and Terraform says, error acquiring the state lock. It means the lock file in your remote backend is currently held by another process or was left dangling.
The mayor is locked out of the city registry office.
Pretty much. The fix, after you've confirmed that no other process is genuinely actively running an apply against that state, is to use that command we mentioned. Terraform force unlock lockid.
Where lockid is some identifier Terraform gives you in the error message.
Usually, yes. You provide the ID of the dangling lock, and Terraform attempts to remove it. But again, use this command with extreme caution. If you force unlock while another process is still running, you risk corrupting your state file badly. Verify first.
Okay, state lock error. Use force unlock carefully. What's next?
The second frequent issue, especially when migrating or dealing with manual changes, is the resource already exists. Error.
This is the drift consequence. Terraform tries to create something, but it's already there because someone did it manually.
Precisely. Your blueprint says create Azure storage account named misstorage, but you run apply, and Azure or AWS or GCP says error. A storage account with that name already exists.
So Terraform stops. How do you fix it? You don't want to delete the existing one necessarily.
Right. The solution here is not to delete, but to bring the existing resource under Terraform's management. You use the Terraform import command.
Import. So you tell Terraform.
You tell Terraform, hey, this resource defined in my HCL code actually corresponds to this existing resource out there in the cloud. Please record that connection in the state file so you can manage it from now on.
How does it know which existing resource?
You typically provide the Terraform resource address, for example, Air's storageaccount.myaccount, and the unique ID of the existing resource in the cloud, like it's Azure Resource ID or AWS ARN. Terraform then reads the existing resource's configuration and saves it to the state file.
So it's like registering an existing undocumented building into the official city registry.
Perfect analogy. crucial for brownfield environments or fixing drift.
Okay, state locks, existing resources. What's the third common headache?
This one can be a bit more confusing. The dependency cycle error.
Cycle. Like A depends on B and B depends on A.
Exactly. Or maybe A depends on B, B depends on C, and C depends back on A. Terraform builds its dependency graph, and it detects a loop. It can't figure out which resource to create first because they're all waiting for each other.
A logical deadlock? Like two people stuck in a doorway, each waiting for the other to go first.
Precisely. Terraform will throw an error saying it detected a cycle involving specific resources.
How do you fix that? It sounds like a fundamental problem with the blueprint design.
It usually is. The fix almost always requires stepping back and rethinking the architecture of that part of your configuration. You need to break the cycle.
Ow!
Often, it involves restructuring how resources get their data. Maybe instead of resource A directly referencing an attribute of resource B, which needs A, you have resource A use a data source, we'll touch on those, to look up information created by B after B is created. Or maybe you need to introduce an intermediate resource. Sometimes careful use of dependent can help, but often it's a sign your logic needs untangling.
Okay, so cycle errors usually mean rethinking the resource relationships. Got it.
Right. Now, to kind of wrap up the core concepts, let's quickly cover 3 more advanced but really useful resource management techniques that help the mayor manage complexity and scale efficiently.
Okay, advanced tools. Lay them on me.
First, let's settle the classic debate. Count versus for each.
Yeah. Both are ways to create multiple copies of a resource, right? Like create 5 identical web servers.
Correct. But they handle identity and changes very differently. Count was the original way. You'd say count at 5, and Terraform creates 5 instances, index 0, 1, 2, 3, 4.
Simple enough. What's the problem?
The problem comes when you change the count or modify the list that the count is based on. If you have 10 servers, 0, 9, and you delete server number 5 from the middle year list,
Yeah.
Terraform sees the remaining servers as needing to be reindexed. What was server 6 becomes 5, 7 becomes 6, and so on. Because their index identity changed, Terraform often thinks it needs to destroy and recreate server 6 through 9, even if nothing about their configuration changed.
Oh, that's really inefficient and potentially disruptive, just because an unrelated item was removed.
Exactly. It caused unnecessary churn. That's why for each was introduced and is now generally preferred.
How does for it work differently?
For each iterates over a map or a set of strings, using the map keys or set values as unique identifiers for each resource instance.
So instead of indexes 0, 1, 2, you might have instances identified by web server John, web server Jane, web server Mike.
Precisely. Now, if you remove Jane from your input map, Terraform knows to destroy only the web server Jane resource. The instances for John and Mike retain their unique identities and are completely unaffected.
Much smarter, much less churn. So use for each over count whenever possible, especially for production.
That's a strong recommendation, yes. It leads to more stable and predictable infrastructure management.
Okay, for each count. What's next?
Data sources. These are incredibly useful, especially in larger or existing environments.
Data sources, are they like resources?
They look similar in HCL, but they serve a different purpose. A resource block tells Terraform to create or manage infrastructure. A data block tells Terraform to read information about infrastructure that already exists and is managed elsewhere, or maybe even by a different Terraform configuration.
Read-only information fetching. Like looking up the ID of a pre-existing VPC or subnet that your current configuration needs to deploy into.
Exactly. You don't want your current Terraform stack to manage that core VPC, but you need its ID. So you define a data source, like data os VPC existing filters, and Terraform will fetch the details of that existing VPC and make them available. Example data.aws_vpc.existing.id for your resources to use.
So it lets your configuration consume information from the environment without taking ownership of those external resources.
Precisely. Essential for connecting different stacks or working within established infrastructure.
Okay, data sources for reading. And the last advanced tool.
Let's quickly revisit import. We mentioned it for fixing the resource already exists error.
Right, bringing manually created things under management.
But strategically, import is also vital for gradual migration. If you have a large, complex environment that was built manually over years, the artisanal city, you probably can't afford to tear it all down and rebuild it with Terraform in one go. Terraform import allows you to incrementally bring existing resources under Terraform management.
Ow.
You write the HCL code that accurately describes an existing resource, like that critical manually built database. Then you use Terraform import to link that HCL definition to the actual running database in the cloud, populating the state file. Now, that database is managed by Terraform. You can repeat this process resource by resource, gradually bringing your legacy infrastructure under the safety and control of IEC without a massive cutover.
That's huge. It provides a migration path from manual chaos to IEC sanity.
It's a critical capability for real-world adoption in established organizations. Hashtag Tape Outro.
Wow, okay. That was quite the deep dive. We went from manual chaos to automated city planning. If you started this feeling a bit lost in the weeds of cloud configuration, hopefully that city analogy helped bring it all together.
Let's do a super quick recap of the analogy. Terraform itself is the strategic city planning system.
Right. The HCL configuration files, those are your detailed blueprints.
The providers Azure, Oz, Google, they're the specialist construction companies who know how to build on specific terrains, translating your plans.
And the state file, terraform.tf state, especially when remote.
That's the single, absolutely critical city registry, the authoritative record of everything that's been built according to the plans.
We covered the power of the declarative approach defining the what, not the how.
The non-negotiable need for remote state and state locking if you're working in a team.
Using modules to create standardized, reusable neighborhood designs for scalability and consistency.
And the core Big Four workflow. Init to set up, plan to preview safely, apply to execute, and destroy to tear down carefully.
You, the listener, the mayor, should now have the language and the practical grasp of these concepts to really deploy infrastructure with more confidence and control.
You're moving away from just clicking buttons in the cloud console hoping for the best. You're architecting. You're building robust, scalable, version-controlled digital systems. It's a shift from reactive fixing to proactive design. It really is a different mindset.
Yeah.
But being the mayor, it's not just about the initial build, right? There's ongoing responsibility.
Absolutely. The biggest ongoing challenge, day in and day out, isn't just getting the city built. It's relentlessly ensuring that your blueprints, the .tf files in Git, and the actual physical city, the infrastructure running in the cloud, never drift apart.
Maintaining that alignment between code and reality.
Precisely. Which brings us to our final provocative thought for you to take away. In a dynamic environment, just running plan when you think you've made a change might not be enough to catch unexpected drift. Relying on manual checks is risky at scale. So the question is, how often should you schedule an automated city survey, basically? A Terraform plan run in read-only mode within your CI/CD pipeline. Not necessarily to apply changes, but just to verify and audit that the registry, the code, and reality are still perfectly aligned. Is it daily? Hourly? That continuous vigilance, that scheduled verification? Maybe that's the real price of managing a complex digital metropolis at scale.